Welcome back to Chemistry Matters Unit 4, Chemical Bonding. Our students have now spent some time creating their own intramolecular bonds with the same tools you found in the Chemistry Matters Toolkit. Now they're going to report their data to their teacher, as well as analyze the patterns they found and investigate how those patterns are important indicators of the types of bonds they formed. So let's get back out to our classroom to take a look and a listen to how they're doing.
Look at the colors and the electronegativity slider bars for atoms A and B. Who wants to describe what you see on the monitor?
I will. Atom A has a very high electronegativity, while atom B has a very low electronegativity.
Atom B has blue around it on one side, and atom A has red around it on one side.
Okay, good. Now, what do these colors tell you?
That the molecule has negative electrons being pulled more to the left side because atom A has a high electronegativity.
And atom B is blue, which means it has a strong positive charge. Atom B also has a very low electronegativity, which I think is why its electrons are nearer to atom A.
Good. You've all worked with the simulations and analyzed the data. So who can tell me what type of bond this is?
The box under the slider bar identifies this compound as more ionic.
Yes, you're right. This is a great example of an ionic bond. Did you collect data so you could figure out what kinds of electronegativity combinations resulted in ionic bonds?
Yeah, we made 10 different simulations that were ionic bonds, and every one of them had electronegativities that were very different from each other.
What was the general range difference in electronegativities that you found with ionic bonds?
We found that when the difference in the electronegativities of the atoms was greater than 1.7, the bond was ionic.
Good. Let's look at another model that I made. Now that you have experience in looking at these molecule drawings, tell me, what do you see in this image, Caleb?
Okay, I see a faint red and a faint blue color. So that means there's a polar molecule with a negative charge on the left side and a positive charge on the right.
Yeah, but they're not really strong charges.
Right, great observations. This is considered a slightly polar molecule. What do you think caused this molecule to become slightly polar?
Does it have something to do with their electronegativity differences?
Yeah, atom A has a very strong electronegativity, but atom B has a little less electronegativity.
So since their values are both high, but don't exactly match, electrons are being pulled more to atom A, which has a higher electronegativity.
That's exactly right. Both atoms seem to have high electronegativities, but since atom A has the higher electronegativity, what would you call this kind of bond?
The bond is marked as being more covalent, so it must be a covalent bond.
Yes, it is more covalent in character than the ionic bond we saw in the previous image. But how does this bond compare to the very first image you saw?
Since the molecule has the red and blue colors, that makes it a polar molecule, so it must be a polar covalent bond.
But we made 12 polar covalent bonds and found a range as we were making different molecules.
Right, and what was that range of electronegativity data that you found to correspond to all the polar covalent bonds you created?
We found the range of differences in electronegativity for polar covalent bonds to be from about 0.4 to 1.7.
Great data analysis. When identifying types of bonds, it's important to identify the actual electronegativity value of each atom if you can. Remember, it's that difference in electronegativity values that helps you determine what kind of bond two atoms will form. For example, if two fluorine atoms, which both have the exact same electronegativity, formed a chemical bond, what type of bond would you predict?
If the atoms have exactly the same electronegativity, there's zero difference between the electronegativity values, right?
Yes.
Then, if there's no difference in the electronegativity between the atoms, they would form a covalent bond.
Good. Do you think it would form polar covalent or nonpolar covalent?
No difference in electronegativity means zero. That means there can't be a polar bond, just a nonpolar bond, nonpolar covalent.
We found that the difference in electronegativity between the two atoms was less than 0.1. The bond was always nonpolar covalent.
Right, well done. Before we leave intramolecular bonds, we need to explore some subtypes of covalent bonds, which will tell us something about their relative strength and stability. Let's look at an example of what is called a single covalent bond. That's a bond in which atoms share only one pair of electrons. Hydrogen, which is number 1 in the periodic table and is the most common element in the universe, forms single covalent bonds with itself and other atoms. Who thinks they might be able to tell me how that works?
I'll try. Hydrogen only has one electron, and for it to be stable like helium, it would need 2 electrons near it. So I guess it would need to share its one electron with another atom to become stable?
Right, nice job. And that's usually the way hydrogen is found, in a bond. When hydrogen shares its one valence electron with the valence electron from another atom, we say there's a shared pair of electrons between the 2 atoms, which is a single bond. Then hydrogen gets to claim both electrons, the one that it contributed to this shared pair, as well as the electron being shared from the other elements. This is why hydrogen exists as a diatomic molecule in nature. It's much more stable bound to itself as a molecule than it is as an individual hydrogen atom, because each hydrogen atom in the molecule has 2 electrons near it. When a hydrogen atom bonds with chlorine, they also share a pair of electrons and form hydrogen chloride, which is used to make hydrochloric acid. Hydrogen chloride has many important applications, from etching semiconductor crystals to making fertilizer. Take a look at this image that shows the formation of hydrogen chloride. All of these images are conveying the same information, with this image indicating what happens just before the bond forms. You can see how hydrogen starts off with one valence electron, but when it shares an electron pair with chlorine, it behaves as if it has 2 valence electrons and becomes much more stable, much like helium has 2 valence electrons. You can also see how chlorine starts out with 7 valence electrons. When it shares a pair of electrons with hydrogen, it behaves as if it had 8 electrons in its valence shell, following that octet rule we mentioned earlier. As these 2 atoms approach each other, a pair of electrons, one from hydrogen, one from chlorine, begin to spend a great deal of time oscillating in between the hydrogen atoms and the chlorine atoms. This forms an area of electron density between the 2 atoms, and it's this area that we call a single bond. Single covalent bonds are usually weak, but are more stable than double bonds. Double and even triple bonds occur when atoms share more than one pair of electrons.
We looked at an oxygen molecule earlier when we were investigating electronegativity. I remember it had 2 lines in between the oxygen atoms.
Yes, I think I have that image here.
Right, that's it. Is that an example of a double covalent bond?
Yes, it is. One line represents a single bond, and as you guessed, 2 lines represents a double bond, in which the atoms are sharing 2 pairs of electrons. Or take carbon dioxide, CO2. That's another familiar compound that has 2 double covalent bonds. Double bonds are stronger than single bonds, but less stable. So what do you think a triple bond would be?
A bond that shares 3 pairs of electrons.
You got it. Nitrogen is one of the elements that can form a triple covalent bond. These bonds are strong but very unstable. The nitrogen molecule is an example of a molecule that contains a triple bond. Each nitrogen atom starts with 5 valence electrons. So when the 2 nitrogen atoms approach each other, the only way for both atoms to become stable is for the 2 atoms to share 3 pairs of electrons. That way, each nitrogen atom gets to behave as if it has 8 valence electrons, again following the octet rule. Larissa, can you indicate on this diagram how each nitrogen has 8 valence electrons?
I think so. 2, 4, 6, 8 electrons for that nitrogen atom, and 2, 4, 6, 8 for that atom.
And I'll bet it takes more energy to break a triple bond than a double bond.
Exactly. But those triple bonds are less stable than the double bonds are.
With that thorough explanation of bonds behind us, let's briefly review what we've learned so far about intramolecular bonds. We learned about ionic, covalent, and polar covalent bonds. To make sure we're really understanding them, we'll create a chart reviewing the characteristics of these bonds. As you can see, when the electronegativity difference between the two atoms is greater than 1.7, we characterize the bond as mostly ionic. If the electronegativity difference between the two atoms is greater than 0.4 but less than 1.7, we call that kind of bond a polar covalent bond. If the difference is between 0.1 and 0.39, it's a mostly covalent bond. And if the difference in electronegativities of the two atoms involved in the bond is 0.1 or less, we generally characterize the bond as nonpolar covalent. As you can see from this chart, though, most bonds can be described as having some percent ionic or covalent character. So while we can give specific names to the types of bonds that hold atoms together, it's more accurate to think about bonding as occurring along a spectrum. Now that we've investigated the forces that occur within molecules, intramolecular bonds, we're ready to tackle the other forces that act between molecules that we mentioned earlier in this unit. These are the intermolecular forces that determine things such as melting and boiling points. We'll be exploring them in the next video on the Unit 4 playlist, so I'll see you there.